Hi folks, Javier Cabezas here. Thanks for joining for this little session about feedback, particularly giving students feedback about their thinking. So let me show you a tweet that Dan Meyer had sent about different types of feedback that maybe we can offer students. So a while back in December, Dan Meyer put out, if we ask a question, please plot the point 4, 5, and a student gives us 5, 4. And we're going to look at 5 different ways that a computer might give feedback on that thinking. And what we really want to focus on is this question. Which of them helps students understand that they are brilliant despite being wrong? So in all of them, they're going to have a wrong answer. We want to know what makes our students brilliant. So let's take a look at the 5 options. So option 1, option 2, option 3, option 4, and option 5. So with all those options, we've explicitly told the student that they're wrong. In the last 2, a little bit more subtly. And so that's what I'm going to try to come forward to today, is walking through. So let me give you an example of explicit evaluative feedback that is typical of what we offer to students. I'll move myself over here to the right. So this is a typical problem. Drag point B so the given line has a slope of 2/3. A check mark will appear when you are right. I'm going to do something purposefully here. I'm going to do down 2, left 3. We see students do that a lot. I know I'm right. Where's my check mark? And that's what I want to think about with how we write our feedback matters, right? I'm a student that has given you an answer, and you haven't provided me any feedback yet. I have no clue what I'm doing wrong. In fact, I'm not doing anything wrong. So I might get a little frustrated. I might call your attention to that as a teacher, or I might just start moving this point or rethinking a little bit. That's where the check mark lives, up 2/3, the most common student move. But what happens if I keep going up 2/3? There's another 2/3 slope. So if I'm in an unprogrammed correct point, this is where we really have to start thinking, what is the unintended harm that we've caused students who are right? And more importantly, what can I do if I'm a student, if I'm a teacher trying to give feedback to students through the computer? Like, how can I get students to continue thinking versus just stop their thinking? I would argue that right now, I don't really have to pay attention to what the problem is. I can just do a little hide and seek, and there it is, and I'm done. I don't have to interact with this. Let's take a look at some interpretive feedback, something with animation. So similar setup. I've got 2 points. This time, place point B so that the line passing through points A and B has a slope of 7/6. Now I want to focus on, what if I just guess something? So I have no clue what I'm doing. I'm just going to put a point. I'm gonna hunt the map. I'm never going to get a check mark to pop up. I have to push try it. And when I push try it, I get this animated feedback. I made a slope of 10/11. Press reset to try again based on what I saw. I know that the answer is somewhere over there. So yes, maybe a student could notice that it was like up here somewhere, but I'm going to challenge and say, does that mean that I'm promoting my thinking or stunting my thinking? I happen to guess it right, but that might be helpful, that a student will pick up on 7/6, rise, run. That works out. And notice what happens if I try a different point. So I'm going to go down 7 and left 6. I'm going to pick it up right here. I think that's 7/6. Let's find out. And when I do that, I can see that I'm on the line. And in fact, the black line is on the blue line. M is 7/6. I made 7/6. I've nailed it, even though I'm in a totally different space. And that is going to be true no matter what I do. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. I'm going to pick non-integer coordinates. And I'm still going to be able to mimic this 7/6 slope. I can be right in many different ways. And that's the power of animated feedback. We can be a little bit more forgiving of what students tell us. So I want to dig into that with you folks today. So thinking back on Dan's tweet and option 5, this is the animation that we're going to work through. We're going to work through option 5 here. Take a point, walk it up. But we are not going to do these line trails behind it. And so to dig into that, I'm going to talk you through how animation works in Desmos Calculator. We're going to build in a calculator today. You can choose to watch. You can build along if you want to split screen. Eventually, just so that you know, you'll have access to this activity where you will, this is what we're going to try to build in an activity. We're just going to build the graph somewhere and link it up in Desmos Activity Builder. And then here in this activity, it's totally no CL, no graph at all. You're going to build from scratch if you'd like to do that. And then lots of different links here as resources. So the first thing is we got to know how animation works in Desmos. And so the first idea is say hi to the median function. So the median function, it just takes the middle value of anything. We all, I think, know that the median is just the middle number in a list of numbers. So here I've got 1, 2, 3, 4, 5, 6, 7 objects. And the median value, if I arrange these in ascending order, is 1. Of course, if I did something else, it would take the average of the two middle numbers. And that's the beauty of the median, is that it just focuses on what's in the middle right now. And so for animation, we're going to use a slider in a 3-element list. And so let me just show you right here. Draw your attention to the median of 0, 1, and z, whatever z is. And we're going to make Desmos interpret this as, is the median value 0%, 100%, 1, or is it some percentage in between? So I'm going to draw your attention to this equals 0. Right now, the median value of 0, 1, and z, since z is -1, is 0. Watch what happens when I hit play. This starts to take on the value of z and then changes it to 1. It's going to play it again. So the median number is 0 so long as z is negative. Then it's whatever z is until z is 1, and then it will stay 1 forever because z is now larger than 1. So you can see that again changing right here. 0, whatever z is, 1. And that is how we're going to make Desmos animate student thinking. So let me walk you through what that looks like. In an animation function, instead of, we're going to take the median value, but I'm going to take the median of a function that I'm calling animate. So for the purpose of this video, I'll add we're used to seeing f of x equals 3x, right? And that draws a graph for us. And the argument is just x, that's my domain variable. Well, for animate, I have 3 inputs that I like to focus on because I find that it helps me think through where I am when I have sequences of animation in different steps. So I'm going to have to tell animate t, which I think represents a running time since a student submits, a start time. So how long after the student hits submit do I want my animation to start? And then from the moment that my animation starts, how long do I want it to run for? So how many seconds until this thing is finished? And I'm just going to take the median value of 0, 1, and that interaction right there. Okay? So here, let's take a look at these steps for animation. Using the animate function notation, I'm going to write 3 steps, something to make the point walk along the x-axis, float up all the way until it stops. And then just to show you that you could then do more animations, I'm going to bring that point back along the path between the origin and where the student told us to go. So just walking through what is happening here. So animate, remember an input, a start time, and a duration. A1 is going to take the median value of t, 0, and 1. T is our runtime, 0 is our start time, and 1 is how long this is going to run for. So in other words, once the student hits submit, after 0 seconds, so immediately, we want this animation to play out and run for the duration of 1 second. That's what this says. A2 is going to be my second step of animation. Base this off of when the student hits submit. I'm going to wait until 1.5 seconds after they've hit submit, which you'll notice creates a 0.5 second pause after A1 has finished. And then I'm going to run this for 1 second. That will be a total of 2.5 seconds of wait time, right? 1.5 from the beginning plus 1 duration, so I'm at 2.5 seconds. So then I'm going to kick my third animation into gear, at the 3-second mark, so after another half-second pause. And I'm going to make this one run for 2 seconds. So you'll see it run a little bit slower. So those are the 3 steps for my animation. You'll notice they all have a value of 0 right now because I haven't done anything to start my time. We'll see that play out in just a moment. What I'm going to do is create this movable point. So you'll notice that, and I'll get myself out of the way here. I got this movable point that I can drag around. So this is usually what we do at Desmos. It's kind of similar to that explicit one, drag the point. But rather than dragging the point, we are going to assign values based on whatever the student tells us to this point. I'm going to force them to be 5 and 4, like in Dan Meyer's tweet. So if a student told us 5, 4, and instead of having that movable point, we're going to control movements. So this is kind of, you can see here, it's a placeholder where in Activity Builder with the computation layer, we're going to overwrite whatever X and Y are based on what the student tells us. So that's just kind of a placeholder for right now. But right now it is 5, 4. And here we're going to start to display movements. So what I want to do is take whatever the student told me and multiply it by A1 and make that go across the x-axis, right? I'm never letting it go up off of 0. And so you can see this note here. A1 and A2 are both 0 initially. So as long as A2 is 0, this point won't display, or will display, sorry. But it won't display until T starts moving. And then A1 is going to walk from 0 to 1. So let me show you what that looks like here. Let's see. X times A1. So if I start to play, you're going to see a point walk across until it gets to the X value. And it's just going to sit there. Then you're going to notice a pause. And then we're going to say, hey, now, once A1 gets to 1, unhide this point. And so long as A3 is 0, so as long as my third animation hasn't started yet, I'm going to walk up along X equals X until I get to A2 of 1, or Y times 1, which is Y, until I get to the student's X comma Y. So this is really 0, 0 until it becomes X, 0. This is X, 0 until it becomes X, Y, because we're at 0% of the student's Y value, and then we're at some percent of that Y value until we get to 100%. And then we're going to walk backwards, right? We're going to be up here at 5, 4. And so when A3 is 0, right, this is the not idea, what we teach students. Sometimes it's hard to know your percentage. It's easier to find out the probability of something happening if you find out the probability that it won't happen and take it away from 100. And so we're going to start at 100 and start walking it back until we get to 0, right? When A3 is 1, then I'll be back at 0, comma, 0, because these two factors will produce 0. We're going to only show that once A2 has maxed out. So it's a lot of info there. And what I want to just show is A1, A2, and A3 changing based off of time. So we're going to watch this go across, up, and then back to the origin. And I'll show you the animation here. It's going pretty fast. I'm going to slow it down. I'm going to take it down to 0.75 speed, which is real time in this case, or 6 seconds. So it's like 1.5 real time. So let's check it out. Across, up, over, with a little pause in the middle. And let me show you what is happening with our animation functions. You'll see that at the origin, they are all at 0. A1 runs, A2 runs, A3 runs. They all stay at 1. And then we reset the timer. And so this is what the 0 to 1 median value is doing. It's running my animations in sequences. So I'm going to pause this timer. You can certainly feel free to run it as 3 different steps. But what I noticed is that could actually all be combined into one movable point, and then we can control it with different sets of the animations. So thinking through, I really have an X and a Y, and I want to move the X for A1, then I want to move the Y according to A2, and then I want to move both of them by 1 minus A3. So I could really just start with my students X, Y input. And since A1, A2, and A3 are all 0 at the beginning, this is really saying X times 0 times 1 minus 0. Well, that's 0. And then same thing happening here. Y times 0 times 1 minus 0 is 0. So I'm going to start at the origin. Nothing is going to change as long as A1 is changing. This is going to stay 0, right? Because I'm multiplying by A2, which is 0. Once A1 gets to 1, I'm going to have X times 1 times 1 minus 0. That's X. Then same thing is going to happen here. A2 is going to increase until I get to Y. And then finally, A1 and A2 are remaining at 1. So this really just reads X times 1 minus 3 and Y times 1 minus A3, which is what we had here in the first place. And I'm just going to hide this until after the student hits time. So now, instead of having open circle, right? These are all open circle animations. I'm going to run the whole thing as a solid point. So I'm going to start from the beginning, and you'll see how I'll turn these 3 off so you really can tell it is, in fact, just this solid point is going to run that animation all by itself. So you can split it into 3 components, 3 different parts, or you can write everything into one point to deliver this animation. Okay, that was a lot right there, and I know I did it quickly, but if you want to reference this, it is on slide 6. This graph is what I saved here. So what I want to do now is take advantage of this graph, right? I want to represent the movement that we just did. So again, we have a solid point that we are moving, and it's all going to be based off of really ultimately this timer T and this movable point XY. And so here's a snazzy little trick that I'd love to share with you right now. You hit save on a graph and you go here to share, you can copy this link. Okay. And when you copy that link, if you go to any open calculator space, so I will edit this activity. You go to any calculator space, in an open expression, you just paste that URL. So I'm going to literally just paste it. It imports everything. So I've built this entire graph when I used to have nothing. And so our graph in to screen 5 for the Desmos activity. And I need to make sure to name my component. So, all right, so now I've got this set up. And when I go here and I enter 5, 4 and plot my point, nothing happens because we haven't told Desmos yet how to talk, how to get the graph to pull the information from the table and how to get the button to talk to the graph. So that's what we're going to do is we're going to set some number syncs. So let me move this out of the way. I'm going to call this table, looks like I already did. And I'm going to call this button, button. And then I'm going to name just a couple of items for the graph. I'm going to say, hey, I need you to listen out for a couple of numbers. The first is number T. T is time. It's time since the button dot time since press. So whatever the time is since you press the button, record that in time T. Okay. The other thing that we need to listen out for is the X coordinate, which is capital X in our graph. We're going to make that whatever the number is that the student writes in the table cell numeric value 1, 1. So this reads, hey, whatever the numeric value is of row 1, column 1 in table, assign that to X. Then we're going to do the same thing for Y. We're going to say, hey, number Y, listen for the table cell numeric value of row 1, column 2. Now that we've listened out for those 3 things, our graph should be able to do something. So let's go ahead and try this out. So when I enter 5, 4, let me move myself out of the way before I push the button. So 5, 4 has been pushed, entered. We push the button and we should see our little dot animate. Let's check it out. We go to 5, we go up to 4, and then we go back to the origin. And we're going to sit at the origin because the time has been pressed, right? I did not change this yet to match the previous example where this changed to a reset button. But if I do something, I can send the message again. I can also stop my animation by clicking in to change my mind. Like, what if I think this should have been like -7 and plot my point? And it would go over there and up to 4 because it's just listening to whatever the student does and it's going to walk it back to the origin. Now, we don't have a target point, so we haven't created exactly Dan Meyer's activity, But we can add a target point, right? I believe the target point was 4, 5. And then this now completes the goal of the activity. Enter the coordinates of the point shown on the graph, see if you're correct. Now we're mimicking what we had in that tweet. Okay, 5, 4. Just a little bit off. Maybe it should be 4, 5. And now we've let the student see they are correct. I just get rid of this third leg of feedback. Couple things. I haven't protected against everything. So what do I mean by that? What happens when a student writes something off the screen? That would be one, right? So like I'll write 1111, which we know is up here somewhere. Sure enough, my point walked off the screen and I lose the benefit of my animation. So I need to be careful and focus this in between -10 and 10, right? I don't want students to give me things that are off the screen that is not helpful to them. So I need to protect myself with an error message. The other thing is like, what if I type in a word like hello? It's not a number. So let me show you how to use some computation layer to, again, try to encourage and nudge students to be able to take advantage of the feedback. So inside of the computation layer for the table, there are two things that I want to occur. The first is an error message, row 1, column 1. And that's going to be when is undefined. So if something is not defined, not a number, then I don't want this to display. So what's undefined? This dot cell numeric value 1, 1. And this is undefined. Say, please enter a number. Otherwise, no error message. Let's take a look at what that means. All right, so let's write something like hello. Please enter a number. That's useful. Okay. What if I do something like this, though? 3 minus 2. It's going to evaluate for me, and I don't have an error message because I can get the numeric value here. So I might disable evaluation. I might leave it. I don't know. For this case, I'm going to leave it. But what happens if I do something like -11? I don't have an error message, right? So now we got to think we're going to add something for our students. I also want this. So when it's undefined, tell them enter a number, or, right? So when it's undefined, or when this dot cell numeric value of row 1, column 1 is less than -10, or this dot cell numeric value of row 1, column 1 is greater than 10. Please enter a number between -10 and 10. And now I've given students good feedback to be able to take advantage of the animation. So here I'm going to enter -11, and then when I go here, oh, an error message. What's that about? Please enter a number between -10 and 10. Oh, okay. Let's make this -1.1. Perfect. My error is gone. I moved on with my life, right? See, even if they're focused in it, please enter a number between -10 and 10. Again, is every student going to see that? I'm not sure. Are we trying to encourage student thinking? Yes, we're empowering them to be able to iterate. Now, the problem, of course, is that I haven't done anything over here. Well, the CL, we're going to copy, drop down a couple lines, paste. This time I want the error message to be in row 1, column 2. And I want that, if I use control, I can click in multiple spaces at once so that I can edit row 1, column 2 everywhere. Okay, so row 1, column 2, row 1, column 2, row 1, column 2. It's the same message. It's just the Y coordinate this time. So I need it to be defined. I need it to be between -10 and 10. So if it's less than -10, give me a message. If it's greater than 10, give me an error message. So that's taken care of that. The last thing I need is a reset label. So when I go into the button component, I type reset label, and I'm just going to put quotes reset. So I want the word reset to show up after they've pressed the button. Now let's take a look. All right, plot my point. I'm going to try -11, 7. I got an error message. Okay. Let me do -4, 7. I plot my point. -4, 7. Okay. I'd like to retry. I can either click reset, or after I see that I was incorrect, again, this third leg is a bonus, when I click into the cell, it automatically resets for me, right? So I understand that this is supposed to be 4, 5. Let's go ahead and enter it. Takes me there, and I was good. So that is the basics of how you can use animation to deliver feedback to students. We can add more from there, but I really just wanted to kind of hook up a connection in the CL between table, coordinates in a grid, and then that time since you've pressed something. With those 3 pieces and the animation function, you can deliver some really, really thought-provoking feedback to students. If you have any questions, please feel free to reach out to me, and happy building and delivering feedback for students.